Great, thanks, Catherine. And thanks to O'Reilly for hosting this today, and of course, everyone for attending. So my name's Eric Day. I'm a senior software architect, recently joined Rackspace, and I'm mainly working on Grizzle there, but I still stay pretty involved in the Gearman community. And as you can obviously tell, I'm going to be introducing some of the basic concepts behind Gearman today and show you how to get up and running with a distributed job queuing system. So the history of Gearman starts at livejournal.com, and they were one of the first websites out there to really experience explosive growth and popularity. And they had essentially one of the first things that came up was a image processing problem. And when they first started looking at the problem, they were processing their image resizes in the following way. They had a number of machines running a web server like Apache, and then they had a script, and they were actually processing and doing the image manipulation inside of that Apache process. And as you can guess, this is going to saturate your web machines with doing image processing when they should be better, possibly serving web pages instead. So what they decided to do was to move towards a more distributed processing architecture that looks something more like this. And this allows them to essentially push all the work of doing that image manipulation to a separate set of machines that were dedicated towards doing it. And then you can actually put a queue in the middle of that as well, so you're not necessarily saturating all those machines and instead just lining up the jobs ready to be done. So this talk is going to focus on, making that switch from, the traditional in-process approach to, pushing things out to distributed systems. And one of the main users of Gearman that's still out there today is Dig, and Joe Stump, who helped install that and get that set up at Dig, had this quote on the mailing list, I think, sometime last year. And the way he likes to think of Gearman as a massively distributed and massively fault-tolerant fork mechanism. And this is, really important to keep in mind because the whole concept behind Gearman is pushing, that in-process processing out to those remote machines. And there's a number of ways that you can do this. And in this talk, we're going to cover the history, some of the basics to get you going, revisit that distributed processing example with the image manipulation, but then look at some of the more popular distributed processing mechanisms such as MapReduce and asynchronous queues. And we'll cover a few different methodologies in there as well, and shows how Gearman is flexible and doesn't restrict you to one particular set of design concepts when you're designing your distributed system. So like I mentioned, it got started at LiveJournal, and Danga was the company behind LiveJournal, and this was Brad Fitzpatrick and a bunch of Perl developers mainly. And Gearman is also related to other technologies like Memcached and MogulFS, which I'm sure you've probably heard of. It was developed to essentially try to scale LiveJournal.com to handle the growth they were experiencing. And the name Gearman actually has the meaning behind it. It's an anagram for manager. And the reason why they chose this is because Gearman pretty much takes the approach that it tries to do the least amount of work possible. And instead it just tries to push the work from the clients out to workers and tries to do minimal processing in the middle and just coordinates that work for you. So a lot of the concepts around Gearman you're going to see, Gearman doesn't do a whole lot, but it does one core piece really well and allows you to build very flexible architectures around that. And right now, some of the larger installations that are running are Dig still has a fairly large set of machines doing a lot of their back-end processing. And Yahoo, or more specifically the MyBlogLog, Yahoo's blogging service, that was architected by Chris Goffmet, who's actually, funny enough, at Dig now, but I think he's probably responsible for the largest Gearman installation, running at over 120 servers at Yahoo still. Then a lot of other companies, obviously like LiveJournal and Deal News, have been picking it up, especially lately with all the recent development. And speaking of the recent development, some of that is some of the main work that's been done lately, especially in the past year, has been the rewrite of the Gearman job server in C. And this is the main piece that I was involved in, writing all the C components for Gearman. And we've also, based on that C library, we've also introduced a number of new language bindings, such as the PHP extension in C. And I've also worked with a number of people trying to get Gearman clients into some of the databases, and also worked with some student groups to, try to introduce new ones. And one student group in particular did the JMS interface. So we're pretty much supported by all the major languages now. So you have a lot of flexibility when you're, if you're thinking about using this. I've also written a command line tool, so you can use Gearman from shell scripts, which is really useful for, really quick hacks, or if you're just trying to prototype some things out. And last year, about this time, I also multi-threaded the job server. So now we're able to handle much higher loads than we could before. We've done somewhere in the range of 50,000 jobs a second on a 8-core Intel machine. So scalability issues aren't really much of a concern now. I've also worked with helping introduce persistent queues to make the job transport a lot more reliable. This is especially important for asynchronous queues when you're just putting a job in somewhere to be done and leaving to forget about it. You want to make sure that actually gets done sometimes, and the persistent queues guarantee that. And we've also experimented with some experimental protocols, such as HTTP, and at some point we want to look at some other protocols, such as memcached directly inside of Gearman. So some of the basic features of Gearman is pretty much all components of it, even though it's written by a number of developers out there, all components are open source under one license or another. I can say that all the C stuff is under BSD, so you can pretty much use it anywhere that you want. Another big feature is that Gearman takes a really simplistic approach to a lot of this. It allows you to, if you look from the protocol all the way up to the client-side APIs, it's really simple, which means we can also make it really fast. There's very little overhead compared to some of the other job processing systems. It's multi-language, meaning you can use it in a number of ways. Say if your front-end web developers prefer to write in PHP, but your back-end guys prefer to write in Python, you can use Gearman as that intermediary to, essentially to share the code and introduce that interface in between them. It allows you for flexible application design. This is one of the things I commented on before, in that you're not restricted to a single model such as MapReduce like you get with Hadoop. You can design it in any ad hoc system that you want, whether you want an asynchronous queuing system, or if you want a more MapReduce-like system, or another concept that I'll show you a little bit is a pipeline processing system. It allows you to really design your application in any way that you need to. It's embeddable, meaning that you don't have to rewrite your entire architecture around Gearman. You can plug Gearman in, in any amount that you want, whether it's just a single job in an existing web script to actually, re-architecting a whole distributed processing system on it. You're able to, essentially plug it in wherever you really need it. And then there's no single point of failure, and we'll get into that a little bit more looking at some of the network diagrams. So some of the basics, it runs on TCP port 4730. The original Perl server that was written by Danga actually picked up port 7003 just randomly. Unfortunately, that's also shared by the AFS3 port range, so I actually applied for official port through IANA. So if you're running the old Perl server and you're switching to the C server, just watch out for that port change. And the basics behind the layout of Gearman is that you have a client, a worker, and a job server. The client is submitting jobs that need to be completed. The workers are processes that can actually perform those jobs. And the job server sits in the middle and coordinates that assignment of the job between the clients and workers. It also does a number of things in there, such as a persistent queuing. If a job were to fail on a worker, it can restart it automatically, and a number of other little features like that. If you're looking at a typical Gearman stack, you can see that you only have to write the application code on the client and the worker. All the network transport, all the smarts in the job server to handle some of that fault tolerance, all that's taken care of for you. So you have to writing pretty minimal amount of code, and then Gearman's able to take care of the rest of you for you. You can see here that, since you support a number of APIs on both the client and the worker interface, you can say, submit a job from MySQL user-defined function on the front end, and then have a Perl or Python worker running on the back end to answer that job that was requested. So this is where that cross-language support really comes into play. Getting back to the point of Gearman has no single point of failure. So as you can see here, this is a typical, somewhat simplified network architecture of how you would deploy Gearman. Think of every one of those boxes as a separate machine, and you have a number of clients running on the front end. Say if these are, PHP scripts running from an Apache process, and they submit something to a job server, some piece of work to be done, and then the workers can pick up work from any of the job servers that they're configured to look at. Now, say if a client goes away, that's really not a big deal. That's not the fault tolerance that you're looking for because, you lost something on the front end. If a worker goes away, there's still a whole host of workers that are fully connected to all the job servers. So you don't have to worry about, losing all your workers. In that case, you're probably going to lose your entire data center and you have bigger problems. But in the case of losing a single machine, it's not going to affect your overall architecture. In the case that you lose a job server, all your workers are still connected to the other sets of job servers that are still running. And clients can be configured to also fail over to other job servers. So even though in this diagram, the upper left client may only connected to the left job server, if that job server goes away, it can reconnect to another job server to keep on running. So we're going to look at a typical hello world example. This is written in PHP. And on the client side, which is the top box, we create a new client object, add the job server that we want to connect to. In this case, we're running everything on a local machine, so we just connect to localhost. And then we run the function do under the client object, and we say, for the function name reverse, send the following payload, which in this case is a string hello world. Now the function is essentially the queue name, or the identifying what type of work needs to be done. And workers will register for that name, and that's how the jobs are matched up in the job server. Now the payload, in this case it's hello world, is just a string, but that can actually be any piece of binary data, and it can be up to 4 gigabytes in size. So you're able to serialize using anything from JSON to Google protobufers, for some of the more complex jobs. But of course you can send a simple string if that's all your application requires. So after running the function reverse with the payload hello world, it just prints the result out of whatever that function does. Now when the function runs, it actually contacts the job server, submits the job, and waits for that result to come back from the worker. So there's actually a lot going on inside of the do, but you can see the interface behind this is pretty simple. On the bottom box, this is what a typical worker would look like. In this case, it looks a lot like the client above, where we create a worker object, add a job server, in this case, the same job server, since we'll be running the Gearman job server on the same machine as the client. And then we add the function reverse. And this registers with a job server saying, like, hey, I can do function reverse, and every time I get a job for that function reverse, I'm going to run this callback function that you can see defined below. And then the workers run essentially as a small persistent daemon in an infinite loop just waiting for work to be done. So you can see it enters into that loop and just keeps doing work as long as there's work to be done. And every time a job comes in, you can see the callback function takes a job argument, which has a number of attributes that you can pull from it. One of those is the workload data. In this case, it's going to be the hello world string that the client sent. And we simply reverse the string, and whatever this function returns is what gets sent back to the client. So if we go and actually execute this, the Gearman D is the application that is the job server, the Gearman daemon. And we run that in the background with the -d flag detaches it. Then we run the worker in the background, because remember that acts as a small daemon in itself, waiting for work to come in from the job server. And then we go ahead and run the client, and you can see it prints out the reverse of hello world, which is what our worker was supposed to do. So getting back to our original distributed processing example of the image manipulation, we were going from this architecture here to this more distributed architecture here. So when an image would come in to the web server, instead of actually processing that image directly inside of that web script, we're going to push that off to Gearman, and then eventually have the Gearman job server push that off to a worker. Now, it's not always the most practical to push every image through the Gearman job server. If you want to actually store that image somewhere, you may push that off to some external storage mechanism. That's what the dotted lines represent here. You may actually say from your web script, go store this over here inside of an NFS or MogulFS store, and then notify Gearman that there's an image over there that I need resizing. So you can either send the image directly through Gearman, or you can store it somewhere and just send a URL or a pointer of where to find that image. And then when the worker gets that request, it can actually go look at that external storage mechanism to pull it and resize, and possibly place the resize image right back there. So through Gearman, you're simply sending URLs to whatever that image location is. So we're going to look at the worker code for that image manipulation program from the last slide. You can see the first 4 lines are pretty much boilerplate for a worker. We're going to register the job server. In this case, we're going to register the function resize, and the callback function will also take a job. But in this case, we're actually sending the entire image as the workload of the job. So this is a case of sending binary payload. We're going to use the ImageMagick library, create an instance of that, read the image blob that came from the job workload, go ahead and scale that image down to whatever size that you need to, and then just return the image blob after that resize has happened. Now if we go ahead and run this, we start up the job server again, run the resize worker in the background, and then this is using the Gearman command line tool that I mentioned before to send a large JPEG and output the small JPEG. So the Gearman command line tool can work as both a worker or a client. In this case, we're running it in a client mode, and we're saying for the function resize, whatever we pipe into this process, that's what it sends as the payload. In this case, we're redirecting the large JPEG into that process, and then any of the output that gets printed from the job gets printed out to standard output, and we just dump that back into the thumbnail JPEG. And you can see here, we turned a 3 meg object into a 32K object. So the guys at Danga, they created this thing, and they're like, hey, this is really cool. This is helping us solve that image scaling problem that we were previously having. Our frontline web machines are much lower utilization, and we actually have a dedicated image manipulation farm at this point. But there's actually a lot more possibilities with Gearman, and they started thinking, what else can we do with it? One of those things that came up, at the time they were describing this as scatter-gather queries, but essentially what it comes down to is a lightweight MapReduce operation. So if you look at how you would implement something like MapReduce inside of Gearman, you can imagine that you can run multiple jobs at the same time from a single process. In this image, it's showing how you could take a single large job from a top client. In that intermediate worker, you take that large job and split it into smaller chunks of work that can be done. You start up essentially another Gearman job for each one of those smaller chunks of work, run all of those concurrently, and then wait for the results. And then that worker can aggregate those results and send some consistent view back to the client of whatever that may be, if it's a summary or some type of merge sort algorithm, or whatever it may be. But this is a very simplistic look at how you could do a MapReduce application inside of Gearman. So in the previous slide, when we were seeing some of the worker callback code, just imagine another set of embedded clients inside of that callback function that's being run for your worker. So the Danga guys were using MapReduce not in the traditional way that you read about in Google with some of the large data analytics processing, but instead thinking of MapReduce operations really lightweight for every web request coming in. And they did this so they could reduce the page load time by basically introducing concurrency into applications or web scripts that are generally not able to be concurrent. So what this allows you to do is push expensive operations off. For example, if you need to run 5 database queries, maybe do some custom ad generation, based on data locality and maybe some information you know about the user. If you need to do any type of data retrieval, outside of a database query, or maybe you just want to improve your caching by, taking some of the approach, some of the concepts behind the approach memcached does by, getting that data locality of, a distributed hash on the back end. You can do some of that same type of thing for instead of just caching, but also for things like database queries and other data retrieval processes. So we're able to push those expensive operations off of just that web script that's running and do them concurrently. So if we have 5 expensive things we need to do, we can hopefully do all of them in the time it takes only to do the longest running expensive thing. So this also allows you to start sending back data from your web request before, before needing to actually block for some of those expensive queries. So this is improving your time to first byte. So looking at how this would work, a request comes into a web server. You start up a script, say it's a Python or PHP script, and the first thing that you want to do is fire off your non-blocking Gearman jobs as soon as you can. Say, you get the user form, the request, and you get the form information from the user, and you start off 3 database queries, and maybe you pull an image and send a job to generate an ad request. Start those as soon as possible, and then start processing the rest of your page as soon as you can. This is starting to send, the initial web page, sending your first byte, and as much as you can. And then when you get to the point on the page where you actually need to block for some of that data that you send in one of those original requests, you block and wait until you get those results. Go ahead and send that result back, and then keep doing this. At every blocking point along in the web page. You keep doing this until you've obviously finished all your requests, and then finish off your overall web request. And this allows you to essentially get concurrency in those web applications, as well as being able to send things back as soon as you're getting them back. So you're not having to block, wait until you get everything back from the database server, and then flush it all out at once. You're actually able to send it incrementally. Another application of MapReduce that I've demoed at some of the Gearman talks is being able to do log processing. Now, when you think about how to do log processing, currently if you have a set of Apache machines, maybe you're pushing all your logs off to a central file server, or maybe you just have a bunch of scripts set up to go and crunch through the logs on the machines where they're actually being collected directly on the Apache nodes. Now, you may not want to do this because you want to keep your log processing separate from your frontline web serving machines. So what you want to do is push those Apache logs off to some other set of log processing nodes that are dedicated just for doing that job. And once you do that, it allows you to do a lot more expensive operations on those logs, where maybe before you were timid to do some expensive log analysis because you didn't want to saturate that Apache node. Now you're able to do that on the separate cluster dedicated just for that. And then, of course, we want to be able to do this, some of these operations in parallel if you're collecting a lot of these logs. So you're able to produce some type of summaries, or possibly doing some type of distributed merge sort algorithms to get one consistent view of the logs for some other type of processing. Now, doing this is essentially 2 steps. First, you need to collect it. And with the Gearman command line tool, this can be extremely simple. If you have an access log, you can simply tail-f the access log, pipe that into Gearman, and then this sends one job per log line entry, essentially, into the Gearman job server. And then on the back end, a worker will be picking up these logs and simply writing them out to that log file. You can also do more advanced things with Apache by adding a custom log entry, which essentially does the same thing. Or you could also write a Gearman Apache logging module, which I haven't seen anyone do yet, but I know a few folks have actually talked about doing that. And so any of those three methods would be appropriate for actually collecting those logs and getting them into some other set of machines just dedicated for the log processing. Next, you're actually going to want to process those logs, and this could be anything like doing a parallel grep. Say if somebody's hitting your website really hard on a number of the machines, and you really want to find out like, hey, what page is this particular user from this IP hitting? You want to be able to quickly grep through those logs and find what users are doing on your website, so you can either react to that, possibly block them. You want to have some power to be able to spread some of that search and analysis through. You can also try to tie this into other log analysis programs such as AWStats or Webalizer, and of course you can essentially create a whole set of scripts around it to do custom data mining for click analysis and clickstream research. So looking at how this would be laid out, the first portion here is just the log collection, and this is essentially what we were just talking about in the last slide. You have your Apache nodes all logging to an access log. Those act as Gearman clients shoving log entries into the job server. Then you have some set of workers that are pulling those entries out of the job server and also writing them to the log on this custom set of machines. The nice thing about Gearman is you get a natural form of load balancing the way that it works. So if a worker is really busy, it's not forced to do more work. It only does work when it's free. So if, in this case, if that first worker machine is extremely busy, the other two worker machines can pick up the load. The Gearman job server won't back up because one worker happens to be busy. Once you actually have all that log data collected, you want to go ahead and process it. So you essentially set up a separate instance of a Gearman cluster. And this is how it would look conceptually, but of course you could share job servers if you wanted to. But what you would do is set up a number of workers that can do specific types of tasks. Maybe they're grepping through that log data, or doing a scan of that log data and generating some kind of summary and sending that back to the client. And then you have clients, which may be command line utilities or maybe web front ends that can query these workers and produce some type of summary result that you want from that log data. And this could be anything from a distributed grep to funneling all those logs into one consistent view of the logs if you really wanted to see all of them processing at once. So they did this MapReduce example, or especially with the scatter gather queries for some of the web processing, and they're like, hey, what if we actually don't always want to wait for the results from these jobs? What if we wanted an asynchronous queue? And this is a really powerful concept, and I'm sure most folks have heard of this, but the nice thing about asynchronous queues is they really help you scale with certain types of applications. In Gearman, asynchronous queues, the original authors named them background tasks, which is essentially the same thing. And the way that it differentiates from the other tasks that we've seen before is that once a job is submitted into the job server, the client is detached and can go away. You don't actually have to wait for that result. So you can say, hey, go do this job, and then I'm going to exit the process and go away. And the job server will keep that job in queue and make sure that a worker performs that work at some point. So you can think about a number of applications where you don't need to do everything immediately. For example, when say in a typical web app that needs to send out an email notification, you don't need to send that email notification out when you actually hit the web page. That can simply go into a queue to be sent out at a later time. Same thing with things like stat counters, re-indexing full text search indexes. There's a number of operations that can be postponed and isn't going to affect that user experience. This also allows you to do better processing of these jobs by allowing for batch operations. Rather than having 5 machines all trying to re-index something at the same time, you can funnel those into a single process and only have that indexing done once. So there's a number of ways you can combine those background tasks to be more efficient when you actually need to process them. So there's this one project that Patrick Galbraith and myself, we worked on, and he wrote about this in I think he has 2 books now, one for Perl and one for PHP, but it originally appeared in the book he wrote on Perl web development of how to build a custom search engine, and this is indexing and then searching that full text index in a distributed way, and it's using either Perl or PHP. Patrick did the original Perl implementation, then I helped do the PHP implementation of it. And it demonstrates how to use asynchronous queues and how to essentially create a pipeline of these asynchronous queues to create a distributed application. It uses Sphinx for the full text indexing, and it can use either MySQL or Drizzle on the back end for the actual data storage. And the Perl version also integrates memcached as a caching layer into this as well. So it's easy to integrate into existing projects, and it's all open source, so you can go to launchpad.net/Narada and pick that up and start playing with it if you want. But the reason why I mention it here is because it really demonstrates this pipeline processing that you can use within Gearman. Now in this image, all the yellow boxes represent Gearman workers. So when you think about a typical submission process, when you submit a URL to be indexed, maybe this is some popular search engine, and you say, hey, go index this so it appears in your search results, that index isn't going to happen when you click send. It's going to be put in a queue to be done at some point in the future. What you're able to do is, with Narada, is to be able to take that, send that into a queue of URLs that need to be inserted. And this first worker, all it does is take that URL, normalizes it, make sure it's a valid URL, does a number of other things, make sure it's not a duplicate of one that's already in the system, and then it stores it inside of the database table. And then if it's unique, it will go ahead and insert it into another queue for the fetch worker. This fetch worker will take that URL, parse it, actually go grab that URL, parses the entire document looking for further URLs, and depending on a set of rules that you have set up, it may decide to go re-index those other URLs. So it's either going to follow based on is it within the same site or a certain set of recursion levels that are available to it. So maybe you only want to search 3 levels deep from the original URL that you insert. So if you just ran it out in the open, it would probably go forever and try to index the entire internet. So what this does is once it parses all those URLs, it inserts those new URLs back into the insert worker. So this essentially creates a small feedback loop between the fetch worker and the insert worker. And then once it actually processes that, it stores the document inside the database, and it notifies the index worker that says, hey, there's a new index, or there's a new document in there, run the indexer when you think it's appropriate. The index worker is running, and its only responsibility is to re-index the document index once it either reaches a certain threshold of new documents that have been entered or some time limit. So this allows you to run that job separately to make sure it's not being re-indexed for every single document, because obviously if you're scanning hundreds or thousands of documents a second, you don't want the indexer to be running that that often. So this is a case where you're able to do batching of a number of jobs coming in to only run it once per larger set of requests. So those 3 workers represent the all the components for getting the data in. There's another worker that actually you can see here from the search blue box. We'll call the search worker to essentially do a request against Drizzle and Sphinx to produce some result set. And this is also where we, it's not described in this image, but this is also where we introduce memcached to have cached results for some of these documents. So this application shows you how you can essentially create a set of workers that all have asynchronous queues, so none of them are blocking for one, to complete some piece of work. Just simply goes into the Gearman queue, waiting to be done, and then goes along this pipeline. So you can see from the URL, from submission all the way to the document that it referenced to it being indexed. So those are some of the basic, models that you can do as far as, MapReduce, simple distributed processing, and asynchronous queues. And there's obviously some other distributed models that you can make work on top of Gearman. But maybe some of you will be able to attend the MySQL conference, because we have a number of sessions there that we'll be able to go ahead and explain some of those concepts further. So looking at Gearman as far as what's next, we've written the job server in C, but one of the things I'm working on now is to rewrite this in C++. And the reason for this is because we're wanting to extend the modularity of the Gearman job server. Right now we have a protocol interface that's pluggable, and we also have a persistent queue interface that's pluggable. But there's a lot more things we want to try to plug into this. And we're thinking that by doing a C++ rewrite, we're able to expose some better APIs for people to extend, because frankly, trying to write the modules in C, it works well, but it's a little bit more error prone, as we've seen as people have tried to contribute certain types of modules already. One of these modules one of the new interfaces we want to introduce with the rewrite is a job result cache. And this is essentially merging some of the functionality of memcached directly into the Gearman job server. So if you ask for a particular job to be done, you can have a set of rules that say, if this job were run and it's already cached, just give that cache result directly from the job server rather than going to run another worker to produce that result. This, of course, takes workload off your workers, as well as being able to allow the clients to get those jobs faster. We want to try to introduce more protocols. One thing that I personally really want to see is more support for HTTP protocol. It's in there now and it's experimental, but it still needs a bit more work to be really robust. It'd be nice to integrate other protocols like memcached directly, and possibly look at others like XMPP and some of the more traditional queuing protocols. We want to make it more secure, mainly for cloud applications. Thinking of simple authentication and some SSL or TLS security layers. Right now, Gearman is essentially designed for a LAN, for a trusted network environment. There's really no security, so if you do want to run this over an untrusted network, you'll want to pipe things through SSH sessions for the time being. At some point, like I said, we want to try to get the TLS and SASL authentication support in there. We want to introduce replication. This would allow you to submit a job to a single job server, and that job server would have a set of rules to make sure this also gets run on a separate set of job servers. And this is really useful for things like work that needs to be done in multiple data centers at the same time. So you want to have multiple copies of that work being done. And maybe this is only for requests that are actually manipulating data, not necessarily just searching the data. We also want to introduce improved stats, essentially be able to mine the Gearman job server to get a better view of actually what's going on. Everything from the average time that it takes to run a certain type of worker, to simple things like the current number of jobs in the queue. You can get some of that information out there now, and there's more details on the website of how to get some of that through the admin interface. But we really want to pump that up to make it easier for people who are using this to debug it and to get more information about the jobs that they're pushing through. And then event notification hooks, being able to put in a stream saying, tell me every time a job failed, for example, and having some running log or some way to access that type of information. And this is all development that's a little slow going right now because a lot of the core developers are pretty busy with other projects, and mainly a couple of us also work on Drizzle, and that's taking a lot of our time. But we're hoping to be able to bump some of these new features out here shortly. So wrapping things up, Gearman.org is the website where you can find references to pretty much every client API that we've been able to find out there. It's not focused on any one project, so you'll see, the C server, the Perl server, the APIs, multiple versions for some. For example, there's a pure Python API, and then there's a Python API wrapped around the C library. And obviously, if you can't get the C library compiled, mainly this is usually a case for people on Windows. A lot of the C libraries are mainly written for Unix-based operating systems. So you may not be able to get that compiled on Windows. So if you're running Windows, you'll want to use some of the pure language APIs. Like there's a pure PHP and a pure Python, and the Java API I'm pretty sure should work on Windows as well. The job server in C right now, I haven't seen anyone port it to Windows yet, so you're again restricted to Unix operating systems. But there is a pure Perl server which you could run on Windows for at least development and possibly even deploy it. I don't know of anyone actually running the Perl server on Windows as a actual production service. We're on Freenode IRC channel. There's always someone around to answer questions. And the Gearman mailing list is fairly active as well, and there's a number of people on there actually using it and not just developers, so they can help answer actual production questions as you have them. And we're going to be at the O'Reilly MySQL conference. There are 3 talks on Gearman there, given by myself and Giuseppe Magzia from MySQL. He's one of the community managers for MySQL, so we'll be giving some talks together there. We're also going to have a booth there, so you can stop by and talk to us. So there should always be someone there to talk about Gearman. It's also being shared with the Drizzle team, so you can come learn about Drizzle as well. And we're also going to, I just was notified, I think it was last week, that there'll be a 3-hour tutorial at OSCON coming up in July here in Portland. So if you're interested in really taking a deep dive into Gearman, it's going to be basically a cookbook of common use cases for Gearman and how to go ahead and deploy that. So I think that about wraps it up. So I guess we can look at taking some questions here.
Okay. Thank you, Eric. That was great. And I do want to let people know that if you register for the MySQL conference and Expo now, early reg is still on. You can save $250. And then we have another discount code, which I'm putting in the chat room, that'll save you an extra 25% too. Oh, thanks, Marcy. You always beat me to it. So, Eric, we do have a few questions, and I'm going to take them in the order they came in. So the first one is a little off topic, but interesting. Andrew asks, do you know of anyone using this for bioinformatics data processing, particularly with R?
As far as I know, I don't think I've seen an R client, and I don't know of anyone actually using it for that particular use case. There's a lot of people on the mailing list that are using Gearman for things I have no idea what they're actually using it for. So they very well could have that as use case. They just haven't vocalized it or mentioned on the mailing list. So I would say that would probably be a good one for the mailing list to see if anyone out there is using it. There's been a number of interesting use cases that have come up though on the mailing list, from doing, using it to coordinate jobs for, back-end video processing for movie studios, down to doing geocoding of images. There's sort of a pretty good variety, so I would definitely ask that on the mailing list, but I'm not aware of any.
Okay, so take that question to the mailing list and see if someone can help you. And here's another question from Bill, and I'm afraid that I don't have the context for this, but I'm hoping you can answer it anyway. How does a worker or server determine if it's busy? And in parentheses, he has CPU load, memory checks, question mark.
So how it works is when a worker registers with a job server, it will essentially go into a list in the job server of available workers that can do a particular function. When a function comes into the job server, when a job comes into the job server for a particular function, the job server looks at that list of workers, and it has status of whether it's actually given a job to that worker or not. So it'll look at a set of those workers that are actually free, of workers that it knows is not running a job, and it'll essentially wake up a certain set of them. So it'll say, hey, I see you that you're not doing a job right now, wake up, and there's a job that could be done. Right now it'll wake up, I think the default is, it should wake up either 3 or 5 servers, 3 or 5 workers, and it's essentially a race of the first worker to ask for that job that came in will be the one that gets it. Now, this model sounds a little bit chatty on the network, But, in idle times, there's a little bit extra chatter. But when the job server is really saturated with jobs to be done, there's always work to be done, that extra chatter turns into more efficient pulling of those jobs. So essentially the workers will only ask for jobs when they know they can actually perform those jobs. The worker's never forced onto the worker saying, like, go do this job, and it's going to sit in a queue for that particular worker until that worker gets around to it. So it's really a free-for-all for whichever worker can get to it first.
Okay, good. Good answer. We have another question, and folks, if you have questions for Eric, please send them now. This one is from Abhinav, and he said, if workers are written in PHP, what's the best way to keep them running in the background?
So a worker in PHP, this has been a hot topic on the mailing list a few times. As you can imagine, running PHP in a sort of as a daemon mode, it's not something you want to do, long term. You'll want to restart that worker every so often because, PHP has some leaks in it. So what you'll usually want to do is put a limit of, say, for this particular worker, run 100 jobs, and then after 100 jobs, just exit, and then have some monitoring process to be able to restart that worker. So this can be everything from a simple shell script wrapper that makes sure that process is always running, to using one of the more advanced monitoring solutions like SupervisorD or a number of other open source tools that can, manage processes to make sure they're always running. So typical deployments, you'll see a machine set up and say, make sure there are always 15 workers of this type running, and then the workers can always just kill themselves off of exit or have another process kill them after a certain amount of time, and then make sure new ones are always restarted.
Okay, and then Akim is asking, for asynchronous processing, can the client monitor job progress? Event notifications? Yep,
it can. Right now, that's only a polling mechanism. So when you submit a background job, you can ask the job server and say, like, hey, is this job yet? Or, there's a simple mechanism inside of the protocol for doing a % complete notification. So a worker can send back status updates saying, I have, say, 3 out of the 15 components of this job done. And it can keep updating that with the job server. So anyone querying the job server can get back some type of status of how far along that job is. And the interesting thing about how jobs work in Gearman is that even if you submit a job as a background task, you can actually reattach to it as a foreground task later. And this is one of the more advanced things that you can do that, it's not always the most useful thing, but, perhaps you want a long-running job to be submitted somewhere, and then you can reattach to that job at a later time and be able to pull down either the result set if the timing is correct, or possibly just pull down some status information if it's still running. So there is definitely ways that you can monitor that job progress for background jobs.
Okay, and then I saw that Nathan asked a question, and Brian Moon has been doing a great job answering all these questions.
Yeah.
But
Brian.
Yeah.
Oh, I was going to say, Brian Moon is, he works at Deal News, and they're running one of the newer, I guess for the past year, they've been running Gearman there to power a lot of their back-end processing for that website. So he's been a really valuable community member, and Gearman has, helped out on the mailing list quite a bit and also contributed some code. So yeah, he's doing a great job answering some of those.
He sounds like he knows what he's doing. So maybe you want to comment on Nathan's question anyway. He was saying, are you able to send objects, struts, arrays, etc., from the client to a worker, or is it simply a string?
Yep, it's a binary payload, and it can be up to 4 gigabytes. Probably don't suggest sending 4 gigabyte payloads to this because that's going to take a toll on your network, obviously. But you can serialize from whatever your application demands. Some of the more popular ones are using things like JSON or XML, packing your data into that and sending that essentially as a binary request. Or you can even use more optimized serialization mechanisms like Google Protobuffers or Thrift as well.
Okay. And I think that's all the questions we have. that looked like a question, but it wasn't. So I think that's all the questions that we have, unless someone wants to shoot one out right now. So I want to say thank you so much, Eric, and we'll look forward to seeing you both at the MySQL conference and again at OSCON. That's really great about the tutorial there. Now,
Yep.
Assuming we want to follow you on Twitter, who are you there?
I can be found as EDayPDX on Twitter, and also if you go to, on the first slide here is my website, oddments.org. If you go there, you can find my Twitter handle, and also reach me directly through email through that website. So
we can find everything about you there.
Yep. Just follow that URL, and you'll find everything about me.
Okay, wonderful. Well, thank you very much, Eric, and thank you, everyone, for joining us for today's webcast. I just want to, it was nice to hear about this and to have such a great audience. And I think that's about it. So I'm going to close out the meeting room now. And
great. Thank you for hosting.
Bye-bye.
Bye.